This lesson we're going to be learning about graphing linear inequalities. So first, with inequalities, it's important to be able to figure out if an ordered pair is a solution. And so inequalities work the same way that linear equations did. The only difference is we have an inequality symbol instead of an equal symbol. So if we're trying to determine if an ordered pair is a solution, we're still going to input the x-coordinate and the y-coordinate in for x and y in our equation. So in this first example, y is less than 4x minus 8. If I input 0 for x and 0 for y, we have 0 is less than 4 times 0 minus 8, and 0 is less than negative 8. This one is not true because 0 is not less than negative 8. So we would say that this one is not a solution. Second example, plugging in negative 10 for y. So negative 10 is less than 4 times 2 for x minus 8. Negative 10 is less than 8 minus 8, and negative 10 is less than 0. This one is a solution because it created a true statement. Last example, plugging in 8 for y. So 8 is less than 4 times a negative 3 minus 8. 8 is less than negative 12 minus 8, and 8 is less than negative 12 minus 8. Think of that as adding the opposite, so negative 12 plus negative 8, or negative 20. Well, 8 is not less than negative 20, so this one is not a solution. Now, getting into graphing linear inequalities, we're going to use the same process we used with graphing equations. And the easiest way to graph them is using slope-intercept form, where we can see the slope of this line, noted by M, and where it's crossing our y-intercept. So this example here, if this were the equation y equals 2x minus 1, we would have our y-intercept at a negative 1, which we can see here at a negative 1. And then the slope is 2. So we would count a rise of 2, a run of 1. So from this point, negative 2, 1, 2 is our rise of 2. To the right 1 gets us this point. You'll note the difference, though, is now in this case we have a dashed line and we have some shading going on. But the graphing of what we call the boundary line is the exact same process we use to graph equations in slope-intercept form. So using this example over here, if this was an equation, we would have y equals 3/4 x minus 2. So our y-intercept is negative 2, meaning it's crossing our y-axis at a negative 2. So down 1, 2, here's negative 2 for our y-intercept. And then it has a slope of 3 over 4. So a rise of 3, 1, 2, 3. A run of 4, 1, 2, 3, 4. Gets us to this point. Note this one has a solid line and shading below the line. So graphing linear equations and inequalities, they're for the most part the exact same method in terms of getting this boundary line. The main difference as seen in the previous two examples is sometimes you're going to have a dashed line and sometimes you're going to have a solid line. A dashed line uses the inequalities less than or greater than. A solid line uses the inequalities less than or equal to, or greater than or equal to. So if you think about it, a solid line means any point on that line is included as a solution. A dashed line, just like an open circle on a typical inequality graph, means it's not included. If there's no equal sign, then any point on that dashed line, so going back to this example, any point on this boundary line that, since it's a dashed line, it is not actually a solution. However, over here, the solid line, any point on this line, would be included because of that solid line, because it indicates an equal sign. And then the shading If your inequality is less than or equal to, you're going to shade below the line, thinking you want to shade all values that are less than that equation, or less than that y-intercept. Think of that on the y-axis. If it's greater than or equal to, you're going to shade above the line. So going back to our two examples, this one is greater than, so we have our dashed line because there's no equal sign, and I'm shading above that y-intercept, or above the entire equation itself. I'm shading all numbers that are greater than this equation. So everything is shaded above that, but it's not included on the dashed line for a solution. Over here we have less than or equal to, so a solid line for our boundary line because of that equal sign. And since it's less than, I want to shade all numbers that are less than that line. So if this is at -2, well, here's -3, -4, -5, -6. These are all less than where this equation is, so I'm going to shade everything underneath that entire line. So let's practice an example. Again, with graphing, we're graphing just like we did slope-intercept form. So in this equation, I can see it has a y-intercept of -2. So it's going to cross my graph at a -2. And it has a slope of a -2. So the slope, actually think of it as -2 over 1. So since it's negative, I'm going to count down to 1, 2, and positive for the run would get me here. So now looking at if it needs to be a solid line or a dashed line, I see an equal sign here. So I am going to draw a solid line between those 2 points. And I'm going to extend this down because I want to do some shading now. So this is y is greater than or equal to everything else. So I want to shade all values that are greater than where this equation is. So the number is greater, -1, 0, 1, 2. This is the side that's greater. So I'm going to shade everything above that line. And if you're ever not sure what side of the equation to shade, you can always choose a test point. And the most common test point that's the easiest to check is the point 0, 0. So right here is the point 0, 0. If I check this equation, my 0, 0 is in that shaded region, so it should be a solution. So if we check with the point 0, 0, I'm going to plug in 0 for y, and then plug in 0 for x. I have 0 is greater than or equal to -2 times 0 is 0, so greater than or equal to -2. This is true, so I know I shaded the correct side of the equation. If I did this point and it was not a true statement after choosing a test point, then I know I shaded the wrong side. But in this case, my test point worked out. The point 0, 0 made a true statement, so I know I have the correct side shaded. One more example. This equation is not in slope-intercept form. So one thing you could do to help you with graphing is to rearrange this equation into slope-intercept form. So again, slope-intercept form looks like this. Y equals mx plus b. So I want my x term to be on this side of the equation. So I would subtract 3x on both sides and get minus 2y is less than or equal to a minus 3x plus 8. I just flip-flop the order of these two because I want my x term first. Next step, I have -2 times y. I want y by itself, so I'm going to divide by a -2 on each of these terms and get y. And since I divided by a negative, this is an inequality, I have to flip that sign. -3 over -2 is actually a positive 3/2. And then 8 divided by a -2 would be a -4. So now I can graph this equation. It crosses my y-intercept, or my y-axis at a -4. And it has a positive slope of 3/2. So up 3, to the right 2. And there's my second point. So again, solid line because of the equal sign. And I'm going to extend this line all the way down. Now for the shading, y is greater than everything else. So since y has to be greater, I want to shade all numbers that are greater than that line. So I'm going to shade everything above that line. And again, since this is a solid line, any point on that line would be a solution. If it were a dashed line, any point on that line would not be a solution. So anything highlighted in yellow and on that line represents a solution to this inequality. Okay, taking a look at this example, x is greater than -5. There's no y-intercept here, and that doesn't look like it's in slope-intercept form of an equation. Whenever you have an equation that looks like this, since it is x, it means all of the x values are in relation to -5. So you would find -5 on your x-axis, and this is actually going to be a vertical line going through these points. Now, the only issue here with the line that I have graphed is that this does not have an equal sign, so I actually need to make this a dashed line. So instead of a vertical line, solid line, this would need to be a dashed line. So I would draw my dashed line because there's no equal sign in that inequality. Now the next part is showing that the values of x are greater than -5. So thinking on your x-axis, if here is -5, all of these numbers to the right are greater than -5. You can see it on that x-axis, -4, -3, -2, 1, 0, 1, 2, 3, and so on. So I want to shade everything that is greater than -5. So everything over here would be a solution. Now, since this is a dashed line, nothing on that line is going to be a solution, but everything to the right of it would be. And one last thing, kind of going along with a solid line and dashed line, if we're identifying all the points that are solutions, the points that are solutions, this point is a solution, it's in the shaded region. We could check it by plugging it into this equation. This point is also a solution because it's in the shaded region. Now think about this point, the point 3, 1. Would this be a solution? This one is also a solution because this is a solid line. If I were to check this point, 1 for y is less than 2/3 times 3 minus 1. So multiplying those, 1 is less than 2 minus 1, 1, less than or equal to. This inequality isn't written right. 1 is less than or equal to 1, so it is a solution. This equation here, inequality, should have had an equal sign because this is a solid line. So this is a solution. 1 is equal to 1, so this one works out.